The end behavior of a function is what happens to the y values of the function for very large values of x, namely in the infinity direction, and for values of x in the negative infinity direction. Okay, so we're looking at what's happening to the graph in the extreme x directions. Let's take a look at a couple of examples. In this first example here, we see that as x gets bigger and bigger and bigger, the function tends to negative infinity. Okay, that means it keeps dropping, dropping, dropping forever as x grows and grows and grows. The way we write that formally is the following. F of x tends to negative infinity as x tends to infinity. Similarly, we see that as x becomes more and more and more negative, the function again is tending down toward negative infinity. So we write f of x tends to negative infinity as x tends to negative infinity. This describes the end behavior of this function. Okay, let's look at this example. We'll start with the infinity direction. As x grows, the function grows. So we write f of x tends to infinity as x tends to infinity. And then as x becomes more and more negative, the function is dropping, or it's tending to negative infinity. So we write f of x tends to negative infinity as x tends to negative infinity. Okay, you should pause right here and try these examples on your own. Okay, these are the answers you should have gotten. So here we see that the function is growing in both the negative infinity and infinity directions. Here the function is falling in the negative infinity and infinity directions. Here it's growing in the negative infinity, falling in the infinity, falling in the negative infinity, and growing in the infinity. Okay, let's take a quick look again at these examples. Okay, so here we went down, down. Here we went down, then up. Up, up, down, down, up, down, down, up. What these examples illustrate is that there are 4 possibilities for the end behavior of a non-constant polynomial. And let's take a look at those possibilities. Okay, this first case is going to happen when you have an odd degree polynomial. In this case, the leading coefficient is positive. Again, in this case here, we have an odd degree polynomial. And in this case, though, the leading coefficient is negative. For this case here, we have an even degree polynomial with a positive leading coefficient. And for this one, we have an even degree polynomial with a negative leading coefficient. Okay, let's do a couple more examples. So let's determine the end behavior of this function here. As I stated just a minute ago, the end behavior of the polynomial is completely determined by the leading term. So we need to take a look at the degree of the polynomial and the coefficient, the leading coefficient of the polynomial. The degree of this polynomial is 3, and that's odd. The leading coefficient is negative. Okay, so odd degree and negative leading coefficient, the end behavior is going to look like this. Or more formally, f of x tends to infinity as x tends to negative infinity, and that's illustrated by this piece. And f of x tends to negative infinity as x tends to infinity. That's illustrated by this piece here. Okay, press pause while you try these 2 examples here. these are the answers that you should have gotten. In this case, we have an even degree polynomial with a negative leading coefficient, so we know the function tends to negative infinity in both extreme x directions. And that's written right here. In case 3, we have an odd degree polynomial with a positive leading coefficient, so we know that this is the end behavior. Okay, so it tends to negative infinity in the negative infinity x direction and positive infinity in the positive infinity x direction. Okay, now let's take a look at a very important question. Why do the degree and the leading coefficient completely determine the end behavior of a non-constant polynomial? Let's take a look at a specific example to see why. Remember that in looking or examining the end behavior of a function, we're seeing what happens for values of x in the infinity direction and values of x in the negative infinity direction. And so what that means is that they're very large in magnitude. So if you take one of those super huge numbers and raise it to the 5th power, there's going to be a big difference between that and, say, raising that super huge number to the 2nd power, and then to the 1st power, and then subtracting 1 from it. So what I'm saying is that for very, very large values of x, these terms are very insignificant in comparison to this leading term here. Okay, so this leading term dominates over the entire polynomial for values of x that are large in magnitude. So the end behavior is completely determined by this, which in that we have the degree of the polynomial and the leading coefficient of the polynomial. Okay, so once again, for values of x that are large in magnitude, lower order terms are completely insignificant. That's like comparing $1 billion to $1 billion and 1 penny. That 1 penny really doesn't make a difference in the scheme of $1 billion. Think of this guy as the penny that you're adding or subtracting from the $1 billion.